Hello everyone, this is A Broken Chain, discovering OPC-UA attack surface and exploiting the supply chain. My name is Eran Jacob. I am a security research team leader at Otorio. Otorio is an industrial cybersecurity solutions and services provider, and along with me on this project worked Roman Dvorkin and Alonzini on the fuzzing part. Let's do a quick overview of what we are going to talk about. First, we are going to start with some intro on OPC-UA and why we decided to research it. We will continue to discover the attack surface of different implementations, and afterwards we will exploit some of the implementations we found. At the end, we will cover some fuzzing work we have done. So let's start. Automation protocols are used in many cyber physical systems. We can find them in factories, critical infrastructures, and even in your company's building. Along the years, many automation vendors have created their own proprietary protocols for these purposes, which cause some issues in interoperability between devices of different vendors. Along with movement toward more connected environments in industrial environments, there were some issues in security in these protocols that were not originally designed for this kind of security. The companies have decided to create the OPC Foundation, which is a consortium that is responsible for open and secure communication for industrial needs. The foundation first created the OPC Classic, which is a protocol that is made of multiple specifications, providing open and secure communication for different needs of the industry. And while it was widely adopted, there were some issues in this protocol. First of all, it is based on the Microsoft DCOM, which is a proprietary and closed protocol of Microsoft, making the OPC Classic not that open. Another issue was the use of dynamic ports, which made firewall configurations very hard for this protocol. Along with some other issues and security concerns, the foundation have decided to create a new protocol. The new protocol is OPC-UA. OPC Unified Architecture is basically everything we could ask for. It is security-minded, cross-vendor, platform-independent, very maintained and very flexible, and of course supporting the Industry 4.0 and smart manufacturing. OPC-UA can be used across the whole industrial ecosystem, starting from field devices in the OT network all the way to the IT and cloud. For example, OPC-UA can be used between controllers, HMIs, up to SCADA, MES, and ERP in the IT network. OPC-UA is also supporting cloud communication, and if needed, it can be used for field-level communication, and with TSN, it is real-time. As you see, OPC-UA provides us with great power, but with great power comes great responsibility. And any compromise of this protocol may compromise the whole industrial ecosystem. That is leading us to the motivation for our research. Well, basically, OPC-UA is the next thing in industrial communication. We can see it is highly adopted by many vendors and many of our clients. And if compromised, it has some significant potential impact, mainly because it is used to connect very sensitive internal OT networks with more external and more exposed IT and cloud environments. Now we can start discovering the attack surface of different implementations. And we are going to start with the specifications. The OPC Foundation provides full and open specifications for OPC-UA. They publish them online, and along with them we can find multiple open source implementations that were published by the Foundation. Most of these implementations are now legacy, but the Dotnet standard that is based on the Dotnet legacy is still maintained. There are multiple other open communication stacks and commercial SDKs available. And if we look on the OPC Foundation website, we can find listed many products that are using OPC-UA. Now, we wanted to check what implementation is used in common products. And we checked some of these products in our lab and found out that Softing and Unified Automation SDKs, along with the OPC Foundation communication stacks, are being widely used. And we found two main variations of them. One is a native version, and the other is .NET. Focusing a bit on the native version of the SDKs and communication stacks, we can see that the UA stack DLL of the foundation is the same name for the Unified Automation SDK. But this was not the same library. Well, this was not such a surprise for us, since Kaspersky also mentioned this subject in a report they have done in 2018, mentioning there are some third-party applications that are using modified versions of the UA stack. We checked it thoroughly and found out that both Softing and Unified Automation SDKs are based on the Foundation original stack, which is now legacy. Looking at the .NET version of these SDKs, we found the same thing. Now, if we go back to our attack surface, we can see that there are some popular commercial SDKs that are based on the foundations, most of them legacy now communication stacks, along with some other open communication stacks and SDKs. We don't have the full details on all the products that are using OPC-UA, but from what we've been able to see, and according to some statements of the OPC Foundation, we understand that most of the products are using commercial SDKs or the communication stack made by the Foundation. Now, if we focus on the upper part in this attack surface, we can see a clear chain of dependency, starting from the Foundation's original communication stacks through commercial SDKs all the way to products made by large vendors. But before we start exploiting this chain of dependency, let's first cover some previous work done in this area. First, we have the OPC Foundation Security Working Group, which is actively working on securing these important protocols, and we even had the chance to meet with them. But there are some independent researches that have been done, such as the research from the BSI that covered threats, specifications, and the ANSI implementation. And they were also able to find memory leak in the Foundation stack. Kaspersky have done another research in 2018 covering applications using the Foundation stack, and were able to find issues in third-party products and products made by the Foundations themselves. In 2020, they published another paper on ANSI fuzzing. Clouty have published another paper recently that is discussing OPC and OPC-UA vulnerabilities. They found some issues in products that are not part of our supply chain. Along the years, many academic papers have been published, and if you are looking for securing your own OPC server or client, I recommend you reading one of these. Well, it is about time for us to start exploiting our supply chain, and we are of course going to begin with the specifications. Looking at specifications, we can find there is a standard OPC-UA connection, starting from a low ACK, followed by a secure channel initiation. The secure channel provides us with confidentiality, integrity, and application authentication. After the secure channel is initiated, we have the session layer, which provides another layer of security in the form of user authentication and authorization. After the two of these, we can send our messages in a secure way, such as read, write, and call. Reading the reference, we looked mainly for areas that may be more risky for implementations. There are many of them, but we focus on three of them. First, we have the complex data types. Some data types in OPC-UA are very flexible, and we decided we can try and use them for exploiting different parts of it. Another area is the flexible encoding. OPC-UA message can contain different coding and even binary and XML together. And the third subject is pre-security messages. Some OPC-UA messages does not require any security. And for example, we have the messages that are used to create the secure channel, or messages that are part of the discovery service. If we are taking these three areas in the OPC-UA, we can try and check if the .NET standard communication stack by the OPC Foundation is vulnerable to any issues in this area. We decided to focus on the .NET standard, mainly because it's the only one that is still maintained, and we found it being used by many vendors and large products. Looking at the .NET stack, we knew that memory corruption issues are not much a thing in .NET, but .NET still doesn't like the function calls. 2D precursion in .NET may cause the application to crash, and here it is very interesting because in the OPC-UA we have objects that are so flexible they can call and contain the same object underneath, making them nested objects. The reference alerts of such risk when describing nested data types. And a related issue was already found in the past in extension object decoding. Looking at the Foundation's .NET stack, we can find the source code many limitations of the nesting level. But we felt this is not very systematic and decided to check it thoroughly. Well, we have a few nested data types in OPC-UA. First, we have the variant, which is basically a union and can contain any built-in data types or array and matrix. Extension object is also an interesting data type. It is a structure container. It can contain any OPC-UA structure in XML or binary. This is very interesting because OPC-UA structures can contain different data types, including extension object itself. Diagnostic info is much simpler, and it's basically just able to contain an optional diagnostic info object. And the data value is able to call variant that can contain another data value. Looking at these data types, we were able to find issue in the variant decoding in the XML decoder of the OPC-UA. Here on the left, you can see the ReadVariant function calling read matrix that is able to call ReadVariant directly without any limitation, allowing us to perform unlimited nesting. This is placed in the XML decoder for the OPC-UA, and all we need to crash the SDK using this is to create a large enough XML, something like this, but much larger. And we need to find a way to get it into the XML decoder. We have done this using the extension objects, which are able to contain XML decoded structures. And using the extension objects, we are able to pivot our way into vulnerable parts of the stack. And using them before channel session security, we are able to crash the SDK before any security is initiated. Here we can see an example for exploitation of this issue in secure channel initiation. We have an extension object in the message header, and we just have to change the encoding for the extension object and append our payload, and we get a crash. But that was not enough for most applications, because we had to find a way to send much larger XML payload. And most of the applications were limiting us by the buffer size. So we used chunks. OPC-UA allows us to send messages in chunks and reaching message size up to 4 to 16 megabytes in the configuration we checked. But chunks are not supported in the open requests. So this time we used a pre-security message, find servers, which is part of the discovery service that is by design not requiring any security. Sending this message with our vulnerable XML, we were able to crash any .NET application we've checked. This 6-year-old zero-day can be found in the OPC Foundation's legacy, standard, and softing and unified automation SDKs. If we try to demonstrate how this can be exploited, Here we have a main site and two remote sites connected to it. And in the middle, we have the SCADA that is communicating with two of the remote sites. An attacker on the main site may be able to send a malicious packet to the OPC-UA servers, making them crash and cause a loss of visibility and control. This action may cause a total shutdown for many factories and can be performed also from a remote site. In this scenario, we have an attacker that has access to one of the OPC-UA servers or man the middle in its network. The attacker can respond to the OPC-UA client of the SCADA with a malicious response and get the same result. Now, let's try and cover another area, again around the XML, but this time with the XML processing library. We know that XML processing in .NET may be a bit tricky on some versions, and we noticed there were multiple vulnerabilities in these areas before, but it was a great chance for us to check the commercial SDKs. Looking for the modified versions, we found in Unified Automation this piece of code, and if we look here, we have an unsafe XML document loading. This allows an attacker that is able to load XML into this function to perform HTTP requests into the internal subnet and leak files from the attack device. Code refactoring reintroduced this vulnerability after it was fixed in the .NET standard, and we can exploit it in the same way over extension object. A scenario for this kind of attack is pretty simple. We have an attacker in the IT network, and we have an internal OT network that is accessible to it. The attacker can send a malicious packet to the OPC-UA server, retrieve sensitive files, and send malicious requests into the internal network. Let's continue with another type of commercial SDK. This time we are going to focus on an SDK that is based on the ANSI legacy stack. We chose Softing CPP SDK, which is used by many vendors and is supporting multiple platforms. The Softing CPP can run on VxWorks, Windows, and Linux, and is made of multiple libraries. On the bottom here, we can see the TNT5 Stack, which is basically an extended version for the OPC Foundation ANSI stack. Above it, we have the TB5 OT that is in charge on stack SDK level processing. And on the top, we have TB5 CPP that is the interface for integrating applications with the SDK. Here we focused on the integration between the extended version of the ANSI stack and the TB5 OT library. An interesting fact is, while the foundation is using C structures for representing decoded OPC-UA objects, the TB5 OT is using a CPP object made by Softing for the same purpose. And if we try to walk through the process from binary message into CPP objects, we can here see that a binary message is first processed by the TB5 stack, validated, and if everything is OK, we get some C structures. The TB5 OT using these C structures for its own purposes, or if interesting, it saves them into CPP objects. Our focus is here. We looked for issues in the transfer from C structures to CPP objects. But finding issues in the CPP object setters is not that easy, because any input for these functions is first validated both by the TB5 stack and the TB5 OT. So we had to find a C structure that is flexible enough to introduce unexpected input to the CPP object. For that purpose, we have the Foundation's extension object. This is how the Foundation C structure of the extension object is looking. This is not how an extension object is passed through communication, but how it is saved in memory. The extension object structure is made of three main parts. The first part is the ID of the contained structure. After that, we have the encoding of the internal structure, and in the end, we have a union that representing the contained structure. If we zoom into the body of the contained structure, we can see it can contain three types of structures. First way is representing the structure in a binary format. This is used for structures that are not supported by the stack. Another option is saving it as an XML element. And because the ANSI stack is not supporting XML decoding, it is basically the same. The third one is an actual decoded structure in ANSI structure that is containing the internal object. And we basically have here two options for encoded body. We must understand that these both parts of the structure must be validated before any access to the body union is done. Otherwise, we may access int32 instead of a pointer. Looking at the SDK object setters, we could find some setters that are accepting extension objects. But most of them were validating both the type ID and the encoding. After looking a bit deeper, we found a few that missed validation on the encoding part, meaning that if we have any option for making the body not a decoded object but a byte string, for example, we may be able to crash the SDK. But we must remember that type IDs that are known by the TB5 stacks are automatically decoded, and all of the types we found were supported by the TB5 stack. We have two options for bypassing it. One of them is pretty simple. It's just using XML decoding for the internal structure, which is not supported by the ANSI stack, and it will be saved as a byte string. Another option we have is using the type ID. The ID of the internal structure can be represented in different ways, and the ANSI stack is supporting only numeric version of it. So if we send a byte string identifier in a specific length, it will be enough to bypass the checks of the SDK and provide us with an undecoded object. Now that we have a C structure that is received by the SDK and is valid on the type ID field but contains a byte string in its body, all we need to do is to find a way to get it through the object setter function. Unfortunately, this was not working for any of the extension objects we used for so far. And all of them were used internally in the TB5 OT without being set into an object. Well, this was kind of an opportunity for us. We wanted to check another area of the OPC-UA, the PubSub extension. PubSub is a new extension for the OPC-UA protocol, and we decided we are going to find a message that is part of PubSub that will be set into a CPP object setter, which will allow us to crash PubSub applications. A word about PubSub. PubSub is a publish-subscribe model for the OPC-UA. It is using UDP packets, and it is slightly different. There are two main usages for PubSub. One of them is through a relay broker that is publishing the messages to many subscribers. This is mainly used in the cloud. And there are some secure multicast option that is used for field-level communication, for example, a sensor publishing information to multiple subscribers. Looking for an exploitable message, we found one message that contained variant and was set into an object setter. Using the variant, we can add any object we want under this variant, including our malicious extension object. And if we try to demo the use of this message, we can see here that there is our publisher on the right communicating with multiple subscribers on the left through a multicast network. These subscribers are constantly keep getting messages from this publisher. And on the right top, we have our attacker, which is also connected to the multicast network. And if he will send our malicious packet, we will see the subscriber crashing one after the other. We were able to find 7 object setters that were not protected against this attack. And we assumed that this issue is not only exist in softing. Looking at the OPC Foundation Code again, we found the same issue in the sample server of the ANSI stack. And we managed to crash it with the same methods we presented. This is about time for us to continue to the last part in our chain, the products. We know products that are integrating OPC-UA are facing different risks. One of them are configurations related, which means that because of the configuration of OPC-UA is so complex, there is high possibility for different applications to miss some important parts and end up with an unsecured client or server. But since there have been done a lot of work in this area and there are many tools for providing these tests, we decided to focus on the integration of the products with the OPC-UA SDK or communication stack. Here we have an image of Unified Automation SDK, and we can see in the bottom our system vendor system. We can see in the bottom the vendor system that is integrated with the SDK through multiple interfaces. Unified automations are defining multiple required interfaces and optional interfaces for the integration process. And we checked IO Manager interface and could see that some products are actually implementing it. But this time, we understood that this issue must be tested in a more generic way. So we used our own made fuzzer. Our fuzzer is a network-based fuzzer that is using structured mutations on the internal parameters and on the packets or message flow. The IO manager we implemented was read, write, and monitor items packets. And we focused on fuzzing the objects that are being passed to the underlying device. We yet haven't found any significant issues, but we are still working on expanding the mutations to be more OPC-UA specific and covering more products. To sum up, OPC-UA is a very powerful protocol, but if compromised, it can be used by attackers targeting cyber-physical systems. And if we look at the supply chain we discovered, any impact to the first part in our chain may impact many products. We used specific parts in the OPC-UA for demonstrating exploitations of the supply chain. For example, complex objects, dynamic encoding, and unsecure messages. But it's still important to remember that OPC-UA is one of the most secure industrial protocols right now, and we only recommend users to use additional security measures and, of course, make sure the configuration is proper. I want to thank Matan Dubroshing for the mentoring in this project, and, of course, Roman Dvorkin and Alon Zini for the fuzzing part. I am Eran Jacob, and feel free to contact me if you have any comments or questions. Thank you.